Hello everyone. So in the last video, we worked a nodal analysis example with a supernode. And what I wanted to do in this video is I want to work the same example, but I want to make one change. I want to define the reference node at a different point and let you see how to um, work the problem, because it turns out it changes how you solve things. But as long as we're faithful to the steps that I outlined, all the math works out the same. So again, step one, you label all your nodes, right? So we have all that already labeled. Step two, select a reference node. So previously I selected it as here, but it doesn't matter. I can select it here. And I decided to go ahead and do that. And you'll see that it kind of changes how things work here. So then you do step three is circle all supernodes that do not contain the reference node. So in the previous video I made, this whole supernode did not contain the reference node that was over here. But now notice how we've defined our ground here. Now the whole supernode is connected to this reference node. And because of that, we don't circle it. We don't even consider it in our KCl equation. And you might think to yourself, well, then how are you going to be able to solve for all of your unknowns? It turns out that if you just follow through the steps, you'll find out that the number of equations you have is equal to the number of unknowns. So this step, I should say, apply KCl to all nodes and supernodes. I should clarify that. Circled supernodes. So because this whole supernode is connected to the reference there, then we don't even circle it. We don't even create a KCl equation for it. So instead, what we'll do is we'll go ahead and apply KCl to all the nodes that we are able to apply KCl to. For example, in the case of node 5 here, we can't really express our currents with these voltage sources here. So let's just go ahead and apply KCl to the nodes that we know we can. And what you'll find is you just keep on going through the steps, you actually have enough equations and enough unknowns to solve for solve your circuit. So let's go ahead and do node 1. Node 1. Okay, sum of the currents into the node is equal to 0. Here we have I1. We want to know how much current is going into the node here. It's oriented this way, so that means minus I1 current is going in. So minus I1 plus the current going into the node through R4, which, because of the way this is oriented, it would be minus IR4. So minus IR4, then plus this last current through R1 here, but again, it's oriented out of the node. We want the current into the node, so it's minus IR3, or IR1. And that's all equal to 0. And then we'll do, what other node could we do? We could apply it to node 3 over here. So let's do node 3. So sum of the currents in. So I2 is going in. So we'll do I2 plus the current going in from R3, so that's because of the way it's oriented, this will be minus IR3. So minus IR3 plus minus IR2. That's all equal to 0. So then our step 5 is to apply Ohm's law to each KCl equation. And notice that there are no other nodes that we could apply KCl to. This is just a single wire here, so that we can't really do that. And so node 3, node 1 were the only two nodes that we could apply KCl to. We couldn't apply it here because we're not able to express the current. We're not able to express the current flowing here in terms of Ohm's law because it's just a voltage source. We could express these currents in terms of Ohm's law because you have resistors, but the fact that you can't here with your voltage sources makes us basically decide not to apply KCl to node 5. But if you just continue through the steps that I outlined in that previous video, you'll find that again, you don't actually need to write an equation for that 5th node. We will have enough equations to solve for all of our unknowns. So the last step, or actually, well, let me go ahead and apply here Ohm's law here to each of our currents here. So IR1 is equal to V1 minus V5 over R1. V1 minus V5 over R1. IR2 is equal to V3 minus V2 over R2. And IR3 is equal to V3 minus V5 all divided by R3. And then IR4 is equal to V1, and this is the reference node here, so it's just V1 divided by R4. So we've done that, and then okay, so then step 6 is to express voltage source values in terms of nodal voltages. So going back to our circuit here, we could say that VS1 is equal to V2 minus V5. VS1 is equal to V2 minus V5. And we could say that VS2 is equal to, because this is the reference node, it's just equal to V5. V5. So now I want you to notice here, to solve this, what you do is you take all these currents here, and then you'd plug that into your KCl equations. So basically then you're dealing with equations that involve the nodal voltages, right? And we know that we have 4 nodal voltages that we are solving for. So that means we need 4 equations. Well, the 2 equations that we need will come from, 2 of them will come from these KCl equations. And then you have 2 other equations here. So 4 equations, 4 unknowns, and then you can put all that together, put it in a matrix, and solve for your nodal voltages. So what's really interesting about this problem, though, with the way that we defined the reference node, we actually didn't have to sum any currents going into the supernode. But in the end, it gives us the same answer. So that's just something to keep in mind when you're solving these problems, is when you apply nodal analysis and there's voltage sources, depending on where you put your reference node, you may or may not have to actually sum the currents into the supernode. So I hope that was helpful, and I will see you all in the next video. Hello everybody, thanks for watching. If you found this content helpful, would you please consider liking and subscribing to the channel? That will help other people find it. And if you won't do it for me, will you do it for my cat, Muon? Named after my favorite subatomic particle, by the way. So, she will be very, very upset if you do not like and subscribe. So please, don't disappoint. How could you say no to this cuteness?